Okay, so I forgot to record. I'm starting to record now. This is what we've done so far. We're talking about the octet rule and how there are 3 exceptions to the octet rule. We already talked about odd number valence, and we're talking about suboctet elements now, which happens when atoms are happy with less than 8 valence. There are 4 elements that are happy with less than 8: helium, hydrogen, beryllium, and boron. And whenever you draw the Lewis dot structures for them, you do not make double or triple bonds. So if you see, you're done with your Lewis dot structure, right? And you see that at the end, one of them is not happy, the central is not happy, don't make any double or triple bonds. Leave it the way it is. Does that make sense, or should I give an example? Okay, real quick. BF3. So boron would have 3 fluorines attached. Boron has 3 valence, while fluorine has 7, but there's 3 of them, so 21, giving me a total of 24. I'm going to subtract 6 from this total, giving me 18. 2, 4, 6, 8, 10, 12, 14, 16, 18. Do you see how I used up all 18 of my electrons? But is boron happy? Technically, no, right? You would think so in terms of like if it was normal. So then you would be tempted to draw a double bond. But again, you do not draw double bonds or triple bonds for the suboctet elements. Boron is a suboctet element, so you leave it the way it is. Does that make sense? Any questions on that? Yeah, you need to know those elements that are suboctet and expanded octet. Any questions? Okay. Expanded octet is the exact opposite. So that occurs when atoms can take more than 8 valence electrons. Okay? There are 5 elements that you know of that can do this. So there are obviously more that can, and we just don't talk about it in this class. So those guys are xenon, krypton, and then SIPs. So what does it mean? What do I mean by SIPs? So let me get a periodic table for a second. Okay. Right, they're in order. Look at them. SIPS. So those 3 guys are expanded, and then also krypton and xenon are also expanded. So those 5 that you know of can do more than 8 valence on their outer shell. Okay, so then I'll put S, Si, and phosphorus. Okay, any questions on that? No, we're good. Any examples for the expanded? We're okay? Okay. All right. So that's octet, right? And again, everyone knows atoms bond to achieve this rule, to achieve octet, to be happy, to be stable. That's the reason why they do that. Okay. Good. Another, I'm going to leave. Actually, I'm not. I'm not going to have this labeled definitions. So I want to go in order of the PowerPoint, so it makes it easier. So what should I'll title this intro. Okay, whatever. Oh. All right, perfect. So now we're moving on to the next part of ionic and covalent bonding, which is naming covalent compounds. Do you guys remember doing that? We didn't spend that much time. Okay, naming covalent compounds. How do you name covalent compounds? Using what? Yeah, what is that called? Di, tri, mono. What is that called? Prefixes. Okay, so I'm going to draw. I'm going to make a table for you with all the prefixes. So you do need to know the prefixes for the exam. They're not given to you. Hey, I won't give you that. So I'm going to, why is it like not? Okay, there we go. Okay, so I'm going to put over here the prefixes. All right. Okay, mono obviously is 1, di, 2, tri, 3, Hexa.
Hexa 6.
Mm-hmm. Hepta.
7. No, yeah, 7.
Uh-huh. Octa.
10. No, 8.
8.
Damn it.
Nona.
9.
And Deca's 10.
I knew that one. I was waiting for the 10.
Mm-hmm. And Deca is 10. Good. So these you have to memorize. There's like part questions about this. There's like a 6-part question asking you to name a bunch of these covalent compounds. So just remember all of the different prefixes. Okay, so I'll make that, put it over here. Okay, so how do we do that? Okay, we name covalent molecules using prefixes. There are 2 rules for naming that we should follow. Okay, the first rule, right? You never put mono for the first element. And the second rule was like what? What did I say? I'll say there's one rule. Because the second rule is about like canceling out like the double vowels. Which, like, for example, if I had diiodide, you know what I'm saying? Yeah. You don't put 2 I's. It would be diiodide, right? That's like the rule. But I'll just say this. Cancel out double vowels of the same letter. So then I'll put an example, which is the one we just did. So diiodide, that's not correct. So I'll put an X. And then the correct version is diiodide. So then I'll put a green check. Good? That makes sense? Okay. 2 rules. So then let's do some practice. Okay, I'm gonna just put a bunch of random like examples. There's not much explaining for this one. It's just, memorizing the chart. So I'll do 3 names and then 3 formulas. And I'm just gonna make up all of these words. I don't even know if they exist or not. I'm just making it up. Oh, thank you. Oh my God, what? Thank you. It's the end of the day,
Yeah.
You guys get it.
Definitely.
Thank you. Okay. Trying to think of more. P2. We can do like P5. So I'm literally just making up these things. Yes. Okay. And then last but not least, let me see one from your exam.
Yeah. 2 more of those.
All right. Okay, so I'm giving you this problem, and then we want to find what either the name is or the formula is, depending on what I give you. Okay, so the first one, B2O4. We need to use our prefix table to determine the prefixes for these compounds. Okay.
Only mono that we don't use with the
Right, only mono will not be used in the first one. So be very careful with that. You will use mono for the second one. Okay? So I'm gonna actually do one like that. So I'm gonna make this mono. Okay. Perfect. Let's use our table. So first things first, I'm giving you this formula. We're doing this one, number 1. B2O4. What's B?
Boron.
Boron. Okay, and boron has how many? What is the prefix for boron? For 2, sorry. Di. So it's diboron, right? Okay, and then how about oxygen?
Tetra, so tetra oxide.
Yeah, so there's four oxygens. Tetra oxide, or if you put tetra oxide, it's correct. If you put tetroxide, that's the actual more correct one, but I'm not gonna be strict with that.
So
It is like, it's not written, like it's there. It's multiple choice.
would you erase the A?
Yeah, tetroxide.
Okay.
Yeah, so if it's like 2 A's and you wouldn't put double A, yeah. Well, because there is a rule, it just depends on the sound. Like pentoxide, it's not pentaoxide, or tetroxide, it's not tetraoxide. But it like it's written correct on the paper, it's multiple choice, so don't worry about that. Third one, what? Okay, number 2, dinitrogen tetrahydride. So dinitrogen, what does that mean? 2 nitrogen, so I'll put N2. And what's tetrahydride?
4 hydrogens.
Right. Okay, so hydrogen 4 times. So this was a question on your ed puzzle, and so many people did this. They put tetrahydroxide. Why is this wrong? It's not tetrahydroxide. It's tetrahydride. Hydroxide's a polyatomic OH. So this doesn't make any sense. It's hydride for hydrogen. Does that make sense? Okay. Good.
What's this?
Huh?
Can you repeat?
Okay, so do you understand the difference between hydride and hydroxide? That's 2 different words. Do you agree?
Yeah.
Hydroxide's a polyatomic OH minus. Hydride is hydrogen. So students were saying that this thing was called dinitrogen tetrahydroxide. That's not true. They're mixing up hydroxide and hydride. It's just hydrogen with an I at the end. Hydride. Okay, number 3. P6I7. What's P? So I'm gonna put phosphorus, but how many phosphorus do I have? So what's the prefix for 6? So hexaphosphorus. Okay, and then I7. What's 7? Hepta, and what's I? Iodine. So heptaiodide. Okay? Ooh, I should have added another rule actually. Okay, 3rd rule. The second word must always end in I. Never the first. So don't put "ide" on the first word. Yeah. Okay. Good. Number 4. Can you just tell me the formula?
S.
Mm-hmm.
S.
Mm-hmm. SO5. You see how there's no mono written for that one S. Does that make sense? You don't write the one. You don't do mono for the first word. How about NH3?
Isn't that polyatomic?
No. It's not a polyatomic. NH4 is a polyatomic. Nitrogen.
Hydride.
And then, yeah, so it's 3 hydrogens. Hydride. Yes. Does that make sense? How about tribromine? How many bromines?
3.
And what about monofluoride? Perfect. So like that. Does that make sense on how we name? Any questions on naming? Okay.
I keep thinking fluoride is more like fluoride.
Okay, good. Next.
None of that. Yes, that's so funny how many.
Okay, so next part is single and multiple covalent bonds. So there are 3 types of bonds that you guys have learned about. What are they?
Covalent.
No. 3 types of covalent bonds.
Oh, polar, non-polar.
No.
Polar, non-polar.
No.
bonding.
3. So what does the title of this say?
Single and multiple.
Okay, so what are the 3 kinds of bonds you can have? Single, double, triple. Single bonds, such as 2 hydrogens attached, contain only 1 pair being shared, or 1 pair being shared. Right? Okay, double, such as oxygen, makes double bonds. Okay, we have 2 pairs. How much is a pair, by the way? So 2 pairs is 4 electrons, right? Good. Okay, triple bond is 3. And then I have how many pairs being shared? Obviously, 3 pairs being shared. Okay, we call triple and double bonds multiple covalent. Does that make sense why they call that? Because multiple lines in the bond. Okay, so this, again, this is a single covalent. And these are multiple. Good? Okay. Perfect. Okay. Oh my god, I forgot the most important thing.
Silly Billy.
The definition of covalent bonding. Duh.
Of course, nobody cares.
Hello? Change. Okay. Yes. All right, what's the definition of a covalent bond? Yes. Yes. Okay, covalent bonds occur when electrons are being shared between? Yes. 2 non-metals. Does that make sense? Yes?
Yes.
Okay, so I just wanted to throw in that definition. Say it again? No worries. I'm sending this out to you guys anyways.
What if I leave like before, can I still put this?
Depends when you
Like,
leave.
chocolate, please.
That's
What
Siri
time?
says.
What time is it? Yeah,
Can you go up
so
for a second?
5
Hmm?
minutes, basically. If like, if you send it to Jonathan, he sent it to me. Since I was here,
Yeah, I guess I'll give it to you, sure.
hey,
I'll be nice. Okay, good. Perfect. Now, everyone understands what a lone pair means and what all that. I don't have to go over it. Okay, good. So now let's get up to the juice, to the meat and potatoes of this chapter. We're going to start off with bond dissociation energy. All right, let's define what that means. What does bond dissociation energy mean?
Energy it takes to break a bond.
Yeah. Okay, energy needs to take up to break a bond. So remember, what's the point of electrons or atoms bonding? To become octet, right? So they become stable. So so they form bonds to become stable, right? So atoms form bonds to become more stable. Do you remember the staircase? Bohr's model staircase, n equals 1, n equals 2, n equals 3. Remember that? So remember, when an electron's on the first energy level or its home energy level, we call that ground state. Okay, what if it absorbs some energy?
It's exciting.
Then it jumps up an energy level, right? And it gets excited, right? And when it gets excited, it has a lot of energy. It's very unstable. It's like moving around super fast. So how can I get that electron back down to ground state?
When it loses
It has to release that photon. Once it releases that photon, then it can go back down to ground state. So remember, all these electrons want to be in ground state, and they want to be stable, and they want to be happy. So they form bonds to do that. So when bonds are formed, energy is released. Okay? So I'll write that down. When bonds are formed, energy is released. Okay? So if I say when bonds are broken, what is it? Energy is? Energy is required. Yes. Good. Okay, so each type of bond has a specific bond association energy. Some bonds are stronger than others, right? Bond association energy is measured in kilojoules per mole. What's joules? Energy, right? So kilojoules per mole. So let's talk about the types of bonds. Again, single, double, and triple. Okay, I'm gonna make a table for you guys. When does what end? It ends at 3:30, but I might have to go over if you guys want everything. Okay, so sorry, so like I need to have these documents pre-prepared in advance to save time. I feel like if I have all this writing down though, it's so confusing to look at. It makes more sense when I write with you. Yeah. Okay. So let's do a table to talk about our bonds. So I'm gonna put up here bond type. Single, double, triple, okay, the strength, and the length. Okay, all of this is related. Okay, so, and then I'll say energy, actually. I should have said energy. Bye. Okay, sorry. And then I'll say energy.
I feel like we learned all of this in earlier chapters for some reason. We did or no?
No. All right. So, in order for us to determine the strength of the bond, we also have to look at the length of the bond. Okay, so before I finish this table, I'm going to go through bond length with you. All right, so when bonds are formed, there are 3 forces that act upon the bond. Okay, 3 forces. So think of it like this. If I were to draw out 2 different atoms, okay, here's my nucleus, here's my shells, here's my electron. I'm drawing random electrons, random elements. They mean nothing, okay? What's in the nucleus, guys? Do you remember? And neutrons, yes. Okay, so I'm just going to do this. I'm going to draw some makeshift protons and neutrons in there. Okay. Here's my nucleus, let's say. And then I'm going to copy this exactly the way it is. And I'm just going to add some different circles so it's not the same element. And then I'm going to add some different number of valence. Okay, sorry. It's taking me so long to draw this out. All right, good. So I have my 2 elements. Again, there are 3 types of forces that occur on these elements when they try to bond. 2 repulsive forces, 1 attractive force. What does that mean? Okay, so I'll write that up here. Yeah. That's fine. You can leave whenever. Okay. There are 3 forces that occur when atoms bond. So we said the first one is a repulsive force. And that's going to be between the electrons. So think of it like this. The green is the electrons. So this is an electron, okay? And this is an electron. Both of these electrons are what charge? Negative. So if this electron gets too close to that guy, what are they going to do? Repel, okay? Repel. That's repulsive. Now, the other repulsive force is if this guy's proton and this guy's proton gets next to each other, well, what charge are they? Positive. So if these two positive charges get too next to each other, what are they going to do? Also repel. Okay, so you have a repulsive force between electrons and you have a repulsive force between the protons.
There was
Okay?
there was an acronym for this, right?
No, not this. Okay? Then we talk about the attractive force. Well, what do you think is being attracted? Yeah, the protons and the electrons. Perfect. Okay, so the third force would be an attractive force. Say it again. Oh, yeah. Let me change the protons. True. That's what you mean, right? This. Okay, good. So then, let's say I have this guy's electrons are attracted to this guy's what? Protons. And then this guy's electrons are attracted to this guy's protons. So what has to happen for them to bond is that these atoms have to be at the perfect distance in order for them to bond. If they're too far away, are they going to be able to bond? No, they're too far. There's no attractive force. But if they're too close, what's going to happen? They're going to repel. So they have to be at the most perfect distance in order for them to bond. And when they get to that perfect distance for bonding purposes, they form that bond, right? They form that covalent bond. They're sharing electrons. Now, that's what you measure as the length. So then you take the distance from the nucleus between the two bonded atoms, and that's going to be the bond length. So remember, there are three types of bonds: single, double, and triple. So a single bond is just containing one line, right? Doubles are 2 lines, triples are 3 lines. Think of it like this. The single bonds are long, thin, like spaghetti, like uncooked spaghetti, very easy to break. As you keep adding lines, you're adding more electrons for sharing, and the length gets shorter. So which bond is the shortest? Yes, so I'm going to put that here. So my length here, this is the shortest guy. And who's the longest? The single. What if I told you that as you increase the number of shared pairs, your bond strength increases? So let me write that down. As number of shared pairs increase, the bond strength does what? Also increases. Oh my god, I cannot write. How do you spell strength? Strength. There we go. Bond strength increases.
Is it bond length like atomic radius? Or
No. Good. I'm glad you brought that up. No,
Is it
not like
thought about
atomic
it when you
radius.
did the nucleus things together, like
Yes. Not like. Similar, but not like. Okay, so look at this. What do I mean by that? In a single bond, how many pairs are being shared? How many pairs? One.
Oh, wait.
Pair. A pair is what? How many?
2.
2. How many pairs are being shared in a double bond?
All 4.
How many pairs?
Wait. 2. Yes.
How many's in a pair?
2.
2.
That's why I said 4.
So here, how many pairs are being shared?
2.
How many pairs are being shared?
3.
So as you increase the number of pairs, so as I'm increasing the number of pairs, what happens to my bond strength? So who's the strongest bond?
The triple bond.
The triple bond. Okay, so I'll put that over here. So he's the strongest, and he's the weakest. And then of course the guy he's just in the middle, right? So I'll just put medium. Okay, now what do I mean by energy? So then bond dissociation energy is the energy needed to break a bond. If this bond is so strong, will it be easy to break? No, so I'm going to need a lot of energy. So usually triple bonds, they go for
Hydrogen and heat, right?
no, you don't have to memorize those numbers. Triple bonds, they're around 945 kilojoules per mole
Isn't joules heat or
energy. Yes. So 945 kilojoules per mole, while double is 498, around 498, and single is 159. So do you see how the energy increases, getting you stronger bonds, right? That makes sense? So what I'm going to give you on a test is I'm going to give you 3 different bonds with these 3 numbers. And you're going to choose, okay, which bond is the strongest? How do you know which is the strongest?
The biggest number.
The one that with the biggest what? Number. Does that make sense?
Yes.
Okay, good.
This is a really
Okay.
good conversation.
Good. So then I'm going to say, okay, I'm going to put on the side. When the atoms are at the perfect distance of maximum attraction, so the most attraction, right? They what? Someone said it? They bond. Okay? Then the distance between the nuclei is the bond length. Does that make sense? Yay. Hooray. Okay? Next topic, resonance structures. Okay, resonance structures. So with resonance structures, that's just a fancy way of saying you have more than one Lewis dot that's correct. Okay? So basically, I'll put here more than one correct Lewis dot structure for a molecule. Okay, let me just check if it's still recording. Yes. More than one correct Lewis dot structure for a molecule. So let's look at an example together. CO2, 3 minus. Sorry. CO3, 2 minus. We draw this guy a lot. Okay, so let's draw this guy together. The Lewis dot structure for him, I would have 1 carbon in the middle with 3 oxygens, right? You guys agree? Yes? Okay. Carbon has 4 valence. Oxygen has 6, but there's 3 of them, so it's 18, giving me a total of 22, correct? I'm going to subtract the bonds, so that's 2, 4, 6, giving me how many left over? 14, right? Wait, 16, yes. Okay, where do I put these 16 electrons?
Around the oxygens.
Wait. Yes, but wait, sorry, I went too fast. That's my total. I'm forgetting I have a charge here. So what does a negative charge mean?
That you have an added electron.
Right. You're gaining electron. What is that called? Anion or cation? Nice. So when I have an anion that's negatively charged, it gains electrons, yes? And what's the charge? 2. So I'm adding 2 electrons to my total, giving me how many now? 24. Now I could subtract the bonds. 2, 4, 6. What's 24 minus 6? Yeah, tap the screen. Sorry, thank you. What's 24 minus 6? I don't get the point of coming to tutoring and being on your phone. I'm just saying. Like, I just don't.
18.
Okay. I'm just saying. 18.
Yes.
Perfect. So where does this 18 go? How many? How many? On each oxygen.
6.
So 2, 4, 6, 8, 10, 12, 14, 16, 18. I used up all 18, right?
Yeah.
But is my carbon happy?
No, but it's
No.
an exception. Right? No, never mind. That's the one that isn't.
Carbon is not an exception.
This is when you make a double bond.
Yes, so now I have to make a double bond. How do can I just add a line wherever I want? No. I have to erase a lone pair to make a line. Because look what happens when I don't erase. I have 2, 4, 6, 8, 10. Can oxygen have 10? No. Is oxygen an expanded octet element? No. He's not. Right? He's not. So I can't have that. Okay, so I gotta make a double bond, but I do that by erasing a pair. Could I put the double bond here? Yes? I definitely could. I definitely could. Okay? So I could have definitely put the double bond here instead. Does that make sense? Okay? Or where else could I have put it?
On the other oxygen.
Right, on the other oxygen at the bottom, yes? Okay? So if I do that instead, right? I remove a lone pair, okay? You're with me? Good. So I have 3 different places to put a double bond. Okay, and I'm going to highlight all 3 of those places so it makes more sense. 3 different places. Okay, but I'm missing something for this, just a side thing. I need brackets for this because it has a charge. Brackets for this molecule because it has a charge. If you don't put brackets, the answer is wrong. No, you need brackets. Yeah. Okay? All right, perfect. So those are our 3 different molecules that we could possibly have for this structure, right? 3 different valid Lewis dot structures. Okay, so I'll put that on the side. More than one location to put a double or triple bond. Either Lewis structure is correct. Does that make sense? Okay. That's what resonance means. Okay, good. Now, did Jonathan leave? Okay, because this is the part that, like, he was confused about that I was going to tell him. Okay, what time is it? 3:14? Oh, we're doing pretty good, actually. Okay, good. So, next part is molecular orbitals. Okay, so I don't have the orbital picture. It's on my computer. Oh, maybe I can take a picture like this. Oh no, I can't draw it, unfortunately. You can leave whenever you want, that's fine. Okay, let me just record this. No. Okay, sorry. Huh? You guys can leave. You don't have to tell me. You can go. It's just free tutoring, right? You don't have to stay here. I'll send it whenever I feel like sending it. I don't know. I really don't know. Because, like, I'm not going to send it to each and individual one of you, right? So then I guess I would just send it in the group chat. And it'll just be there. Because then I have to type in every single one of your emails, and I have to check that. I'm not doing that. You get what I'm saying? So it would be in the group chat if I were to send it, which I am going to send it. Bye. Okay, good. So molecular orbitals, let's talk about them. Remember, we learned about this in chapter 5. So there are 4 different subshells: S, P, D, and F. How many orbitals does S have? Do you remember? How many orbitals? 1. Look at the picture. How many shapes do you see here? So S's have how many? Okay, for P, how many shapes do you see here? 3. So P's have 3. So D's have how many? So you're counting the graphs, really. Okay? And then F's have 7, but we don't care about that. Okay? So molecular orbitals, basically, what I want you to know about this slide is that there's a definition that you have to remember. Okay? Okay, so, and I'll put an orbital. I'm going to say the definition is a bonding orbital belonging to an entire molecule. So what the heck does that mean, right? Let me give you an example. So hydrogen, right? Hydrogen is an example. Do you guys know what the electron configuration for hydrogen is? 1s1. What letter do you see that in that? Right. What shape is S? Circle. Okay, so I'll draw that. H's have a circle, right? And in their circle, in their orbital, right? By the way, these are electrons. In this orbital, I have electrons in there. Remember how we have arrows for the electrons?
Yes.
That's what that means. There's electrons in there. Remember, one S's, they have 1 orbital, right? P's have 3. So let's say I have, 2 electrons on here. I have 1 electron over here, and I have 1 electron over here. Oh my God, stop moving. 1 electron over here. Okay? What I mean by that is take a look. In the S orbital, how many electrons do I have? 2. So I have 2 electrons in that orbital. Okay? 2 electrons in that orbital. Here, this is an orbital. Watch. This is an orbital. Okay? So this guy right here is this. This guy right here is that. This guy right here is this one. So in the green one, how many electrons do I have in the green one? 2. Look at my arrows. How many arrows is in that orbital? How about in the orange one? How many electrons? 1. And how many in the pink one? 1. That's what it means by I have these electrons in the orbital. It's in this shape somewhere. Floating in that shape. That's just an area of space where it could be. So if I have hydrogen with an s orbital, right? Remember, what does the s look like? A circle, right? And I have 2 hydrogens with 2 s's. Again, each one of these hydrogens has 1 electron available for bonding. You're with me? Okay, so when they overlap their orbitals, watch. When they overlap their orbitals, what happens? Bye. It forms this bond, right? That's the bond that's formed, the line that you see. This and this are the same exact thing. This and this are the same thing. That's the bond. Yes. Yes, an H2 because it's diatomic. That's the bond. Now, we called this a molecular orbital because it's an orbital of the molecule. An overlapping of the orbital of the molecule. Does that make sense, guys? Okay. So then what I want to talk about from this is going on to what oh, I don't have to talk about that now. Okay, good. Good. So you understand what I just did? Yes. So Nova's definition, right? A bonding orbital belonging to an entire molecule. So when the orbitals overlap, okay, bonds are formed. Again, I drew out the 2 S circles. You're with me? So, sorry, move this letter here. Okay, so S is the circle. Do you see that? That's why I drew a circle around H, because it only has an S. If its S orbital has an electron on it, in it, and then it interacts with another S orbital, and they overlap, electrons can be found in this overlap. That's the bond. That's how bonds are formed. Okay, so basically, that's what I wanted you to know about that, just the definition. Okay, the next part of the slide are sigma and pi bonds. Sigma and pi bonds.
Is this what we need to know to figure out the sigmas and pi's?
Yes. Well, you're welcome. I'm actually gonna not go through sigma and pi all the way through because I showed like videos in class and I had like a whole explanation. I'm going to give you a very brief explanation, not like deep, because you don't need to know the deep aspect of sigma and pi, just know how to count them. Okay? But what you should know about sigma and pi is I'm going to have 2 different headings for them. Okay? Sigma versus pi. Okay? So what you should know about sigma first is that it's a end-to-end overlap of orbitals. What does that mean? Okay, so there are 3 ways that sigma bonds can happen. Okay? Let's do an example. The one we just did, hydrogen. Hydrogen had 2 S's, right, guys?
Yes.
Well, one hydrogen had 1 S, one had another. Do you see how it's overlapping here? Okay, let's say I were to give you another one, HF. It's going to make sense in a second. Let me draw it out. Okay, again, let's talk about the electron configuration for hydrogen. It's 1s1. And then for fluorine, it's 1s2, 2s2, 2p5. Okay, so we said that we're using the S for hydrogen because it's the only one he has. But you see how fluorine has S's and P's? You use the most recent one, the most new. Which one is it? The P. So he's going to be the bonding guy. Okay? P orbitals, what do they look like? We draw them as dumbbells. So this is what we represent P orbitals as. Dumbbells. So if you see that, I'm talking about a p orbital. Does that make sense? There's 3 different ways they can be in 3 different orientations, 3 different directions. So here for the fluorine, I have a p, right? And for the hydrogen, I still have the s. Does that make sense? So I have a p orbital here, and then I have an s orbital here. And now you see how they're overlapping. So I have the p from the hydrogen, the p from the fluorine, the s from the hydrogen, and they overlap in this region. That's their bonding orbital, their molecular orbital, and that's where the bond is formed. So that's where this bond happens here. This is called end-to-end overlap. Do you see how my p orbital is laying down? It's like this. That's end-to-end. I can also have p to p. So if I have f to f, for example, so then I'll have 2 dumbbells like this. It's hard to draw these. Okay, when I have 2 dumbbells like this, sorry, it bothers me. Then I have the 2 electrons in here, and again, it's head-to-head overlapping. So there are 2 ways to do sigma bonding. Okay? S, 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 P, P, P. Okay, now I'm going to make this picture a lot more understandable. Pi, on the other hand, is whenever I have the p's sideways. So this is sideways overlapping of p's only. Hello. Hola. Vertical sideways overlapping of p orbitals only. So there's only one way for a pi bond to happen. This way. Okay? Overlapping occurs here. It's still 2 electrons being shared. So do you see how here it's end to end where my p's are going like this? Right? And then what happens in the pi? It's going up and down. That's the difference between the 2. There are 3 ways to sigma bond, but only 1 way to pi bond. Mm-hmm. Yes. Yeah, I'm just doing a YouTube video. I'm going to upload it on YouTube. It'll be 45 whatever an hour long. If someone wants to watch it, they can. If they don't, I don't really care. Yes. Okay, good. So, this is background knowledge. Now, do you need any of this information to count pi and sigma bonds? No. No, you don't. But the explanation I gave in class was so much better, and since I'm short on time, I'm really rushing it, and I sound like I'm just talking a bunch of nonsense. But I showed videos in class and animations, and it made it click in students' head. But I don't have time to show you those videos. So, you're just gonna have to take my word for it. And when I tell you, you want to memorize this part. So memorize that sigma is end to end, while pi is sideways overlapping. That's super important. Okay, if you're gonna memorize anything of this part. So that's what I would prefer. And of course it's PO orbitals only. And then of course this one is P and F. So I'll add that. Of S and or P. Okay? Now, how do I count pi and sigma bonds? Okay, so I'm going to give examples on how to count them. I'm going to draw 3 Lewis dot structures. Just random ones. This should be fine. Okay, the thing that you want to know is that there's a little key. There's a little trick of remembering this. Okay, so the key is single bonds. Single bonds contain a sigma. Double bonds contain a sigma and a pi. Triple bonds contain a sigma and 2 pi. So that's the key in remembering. Okay, perfect. Now, I can use this key to count all the sigma and pi bonds in my molecule. So let's say I want to count the sigma and pi bonds here. I look, well, we already said that the single lines are what? Plain sigma. I'll move it here for now. Plain sigma. Right? So I have sigma bond here, sigma bond here, sigma bond here, in red, sigma bond here. You're with me? How about the double bond? What does the double bond contain? 1 sigma, 1 pi. So the first one is a sigma, and the second one is a pi. Pi, thank you. Okay, so I have pi, and then I have sigma, 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 sigma. So how many sigma bonds do I have? How many? Nice. And how many pi? 1. Easy, right? Okay, over here, a single one is what again? Sigma. And then triple contains a sigma and 2 pi's. So this guy has how many pi? 2. And how many sigma? Easy, right? Okay, this guy over here, I have only what? Single lines. So how many sigma do I have? Yes. Do I have any pi? No, I need triple and double bonds for that. Does that make sense how I do that? I don't need to go more in depth for that, do I? If I do, let me know. Dominic, you're good? I'm so boring, huh? Trust me, I'm tired of hearing myself talk. I'm ready for this to be over. Just as much as you. Okay, but we're okay with this? So no one has any questions about counting these, because there are a lot of questions on this. All right. I know. Okay, Vesper. Vesper theory. All right, what does Vesper stand for? Do you know? I'll tell you if you don't know. Valence, shell, electron, pair, repulsion. That's what Vesper means. Like, no one's going to say that every time, you know, it's too much words. Okay, and this theory states that atoms in molecules want to be as far, oh my God, as far apart as possible, since their electron clouds repel each other. These atoms adopt certain shapes depending on how many bonds or lone pair and lone pairs are attached to the central. Bye.
Thank you, Miss.
You're welcome.
For your time.
Thanks, guys. Have a good day. Okay, so, are you guys have any questions about Vesper? I don't know. Like, I feel like it's good because the table kind of, yes, this is linear, tetrahedral, that type of thing. So I'm gonna real quick put the picture of a table in the document so we have it. And this is given to you on the test. Okay, so you don't have to worry about memorizing this. It's given to you on the test. The only thing that's not given in the reference sheet is the hybrid orbitals. That you have to know how to do. Okay, so, like this part, not on your test. Not on your sheet. Sorry, why does it look like that? Let me fix this. Not on your sheet. What? Yeah, I did. I don't have Wi-Fi when I'm connected to this like screen recording, so I can't go to the internet and download the picture. So I have to just do this. Okay, so that's not on your sheet for the exam, so make sure you know the hybrid orbitals. Okay, now, are you guys comfortable if I were to give you a Lewis dot and I were to ask you to draw it and tell me the shape? Would you be comfortable doing that? What part do we not have that we're not comfortable with? So, like, for example, like, remember in class today, I'm gonna give some examples. Like, you guys are comfortable drawing the Lewis? Like, do I have to walk you through it, or are you guys good with that? You're okay with it, Sebastian? Like, if I were to say draw the Lewis dot for this, could you do it by yourself? Why?
Yeah, I think so.
What do you mean you can't? You know. Step 1, identify the central atom.
I know the rules, but sometimes when I do it, something doesn't add up or like.
Because you're going too fast. You have to be careful with what the valence are.
But my math would be right. I swear it would just be like the dots and the vertical.
Yeah, so the problem is that placing the dots towards the end is what trips up every student. So, like, for example, okay, I have carbon in the middle. It's my central atom. Hydrogen on one side, nitrogen on the other. That's easy. Everyone knows how to do that, right? Hydrogen has 1 valence, carbon has 4, nitrogen has 5. This is giving me a total of 10. Again, easy. Everyone knows how to do that. I now have to subtract the ones already being used. People forget to do that. That's important. You don't forget. Good. I'm subtracting 4. That means I have 6 left. These 6 must go to the outside first. Must go to the outside first, and you have to make them happy. Who are the outsides? H and N. Is H happy? Yes. So I don't put anything on H. Is N happy? No. How many does he have right now?
2.
Perfect. How many more does he need to be happy? That's perfect. So I put 6 of them as lone pairs around the nitrogen. So now, did I use up all my 6? Yes. But is everybody happy? No. So if you take a look at your carbon, everyone also forgets to check their central atom to see if they're happy. They do this and they forget to check. So most of the time, the middle element still won't be happy, and you might have to form some double and triple bonds. So if my central atom still isn't happy, I have to double check, right? It has 4, so it's not happy. It needs 8. So I got to take some lone pairs from the nitrogen, and I got to form extra bonds to make him happy. I cannot just draw lines wherever I want. I have to erase them. So if I draw a line, I have to erase a lone pair. Is carbon happy now? No, he only has 6 still. So I need to draw another line and erase another lone pair. Is he happy? Yes. So then, again, this is given to you on the exam. You just won't have the SP3 stuff. So I'll teach you how to do that in a second. So how do I know the shape? Remember, you're trying to identify total pairs, lines, lone pairs. So how many things are touching my central atom? 2. 1, 2. So my total number of things is 2, okay? How many of those things are lines? You don't count the individual lines. Does that make, you're not saying it's 1, 2, 3, 4 lines. No. It's 1, 2. 2 of them are bonds. So 2 of them are bonds. And how many lone pairs are on my central atom? 0. So the code is 220. And what shape is 220? Linear. So you have all this information for you. You have linear, you have 180. So you just have to write it on the paper, right? So that's easy, right?
All of that was fine. It's just, I think, when you gave us on the worksheet, I think it was oxygen and somebody with carbon.
Carbon, okay.
I couldn't figure out I was trying to form 4 bonds. Like, I couldn't figure it out.
Which paper? Which worksheet?
The day of the drill. It was like,
When I was absent?
yes, that whole sheet, I couldn't even complete it.
I put some hard ones in
I
here.
could not.
Oh, was it this? CO?
Yeah.
This guy? Okay, want to do this guy real quick? Okay, so CO, who's the central atom? Yeah, because he's in the middle, right? Sorry, he's not in the middle. He's farthest away from fluorine. Okay, so I'm putting him in the middle, attached to O. Now, carbon has 4 valence, oxygen has 6. Total of? I gotta subtract what? Giving me 8. Central atom. So who's the outside guys? Okay, so I gotta put everything on the outside guy first. 2, 4, 6. Wait. Okay. Yes, 2 left. Sorry, I blinked. 2 left. So I used up 6 on my outside guy, and I have 2 left. So anything left must go central. Can carbon take any extra electrons right now? Yeah, how many does he have right now? He only has what? 2. So he can definitely take 2 more, right? Good. Okay, so then, is he happy though? How many does he have?
4.
And how many does he need? So oxygen's going to be very nice, and he's going to form a double bond. But is he happy? No, he only has 6 still. So then he's going to form another bond. Triple bond. Is he happy now? Yes. He doesn't, it's the same steps. What do you mean? Like, carbon is the central. It's the central. So you have only one thing attached to it. Okay, good. So that's the answer. Now, how many things are attached to my carbon? 1, 2. It's the same exact situation here. Does that make sense? Okay. So then you use that for the shape. Are you guys comfortable with hybridization or no? You want to go over that real quick? SP2, yeah. We're good with that one, or I'm gonna put it in the doc anyways. Okay. So hybridization. All that means is a fancy word for saying, orbitals being mixed together. Okay, so if I have an sp hybridized, I have one S and one P was mixed together. They overlapped, basically. Does that make sense? Okay, if I have sp2, for example, I have one S and 2P. What do? Mix together. Does that make sense? Now, do I have to understand how they're mixed together? No, I just need to understand how to identify hybridization from a molecule. So there's a table for that, right? There's a table that's in the PowerPoint. So no, this is different. Yeah, this is different. Yeah, so were you here the day I taught it? No, right? This. Okay. I can give you the long explanation as why it's S and P, which it might make more sense. But are you guys cool with that? It's going to take me like 2 more minutes to explain. Okay, so think of it like this. Carbon. He has this configuration. Okay, if I were to draw carbon as a Bohr's model, it would look like this. Okay, that's because carbon is on the second energy level. Sorry, the second period. What's a period on the periodic table? The rows. So carbon's on the second period. So it has how many shells if it's on the second period? 2. Two circles around. Does that make sense? If it was on the third period, it would have 3 circles. If it had fifth period, 5 circles. You get it. Okay? So let me draw out real quick the orbital notation diagram for this. 1s, 2s, 2p. Do you guys remember this? So s's have how many orbitals? 1, so I put 1 line. S's have how many orbitals? 1, so I have 1 line. P's have how many orbitals? 3, so I have 3 lines. How many electrons goes in 1s here? Perfect. And 2s? Perfect. 2p? 1 in each, right? Okay, so do you see carbon, however, this is the funky part about carbon. Carbon can make 4 bonds. Every time I see carbon, he's attached to 4 things sometimes, right? You know what I'm talking about? So, like here, right? Carbon can make up to 4 bonds. Can I put another bond on him? No, because then how many will he have? 2, 4, 6, 8? That's too much. So the most he can make is how many bonds? 4. But do you see, according to his orbital notation diagram, he can't make 4 bonds. How do you make a bond? If I'm a hydrogen guy with 1 electron, and here's a hydrogen guy with 1 electron, they both want 2 to be happy, right? So what are they going to do, you think? They're going to share, right? They're going to share and they're going to bond. So in order for them to share these 2 electrons, you got to get 1 from him, and they share them and they form their bond, right? But how many does carbon have by himself for bonding? Do you see how he only has 2 by itself? There's no electron in this orbital. So let's say, a random element comes in and they have their little electron. They put it here. This is sharing. They're sharing this. So do you see how I only have 2 electrons who are available for sharing? Can I put another electron here on this orbital? No, it's already full. I can't share with those electrons. They're already paired up. I can only share with these. So with that being said, carbon should only be allowed to make 2 bonds. Does that make sense? But it doesn't. It makes 4 bonds. That makes no sense. Do you understand where I'm going with this? So then that's where it comes hybridization, right? Orbitals are mixed together to be able to do these and be able to make more bonds. So watch this. This is what carbon does to make more bonds. Remember, this 1s is the first energy level. Does this first energy level bond? No. So I don't care about this right now. Okay? I care about these 2, my second energy level electrons. So so carbon is going to do something called electron promotion. This is a part of hybridization. In order for them to mix, they do this. This electron will be promoted over to the empty orbital over here. He just does that. That's what just hybridization is. Okay, so he moved this little electron and he moves this way and he flips up like that. Now he's here. He promoted his electron from the lower energy level to the higher energy level. So now do you see how I have these 4 electrons by itself? Now they're all able to make bonds. Okay? Now, it's no longer 2s and 2p though. It becomes something different. Okay? So how many orbitals do I have here? 4. 1, 2, 3, 4. I have 4 orbitals. So I'm going to draw. I have 4 orbitals over here. And again, they all have 1 electron in them, correct? But these orbitals are not 2s and 2p anymore. Okay? Well, how many s's do I have? This is what? 1s. And how many p's? So now this new orbital is sp3. 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 So now carbon just hybridized his orbitals and he made 4 brand new orbitals called sp3 because he mixed together an s and 3 p's. So now that's why you see sp2, sp3, sp3d, stuff like that because of this. Okay, so I'm going to move this over here for a second. Okay, and now I'm going to go back to my table. So again, there's only 1 s, right? There's how many p's? 3 p's. So I keep adding every time. After the 3 p's, what is there? D. If I added another 1, what would it be? Another D, right? How many D's could I go up to? 5. Amazing. Okay? So then now I have all my different hybridization. We don't spell it out like that. It's just we simplify it to be like this. These are the different types of hybridizations that these elements can make. Okay? And depending on how many things it's bonded to, that's how you know what hybridization it is. Okay? So if I were to go back to this, to find the hybridization of my central atom, of my molecule, I have to see how many things it's attached to. Well, how many things is it attached to? 2 things. The hybridization must match the number of groups. Again, how many things is it attached to? 2. So how many letters should be in my hybridization? 2. which one has 2 letters? So that is an sp hybridized carbon. Okay, if I were to do this guy, okay, this carbon right over here, and there's a lot of writing on it. How many things is he attached to? 3 things. So how many letters should I have in my hybridization? 3. How many letters? Which one has 3 letters? This one, right? Which is what? So it's a sp2 hybridized carbon. Does that make sense? Good. Okay, and that's how you do hybridization. Oh my God, we're not even done, guys. We still have polarity and electronegativity. This is painful. I feel bad for you guys. You want me to go through it? Yeah, I mean, we might as well just finish it off. It's like, what, like 4 more slides?
Well, I'm here until 4:30.
Perfect. Okay, so I'll get through. I'll try to go as fast as possible. Okay. This is a good document, huh? Just charge money for this document. Just joking. Okay, so bond character and polarity. There are 2 very important words you should be aware of. Polar, nonpolar. Okay? Polar versus nonpolar. When I have a polar bond, my electrons are being shared unequally. I'm going to write that. And then I'm going to explain it. Yeah, I'll write it. And then nonpolar, well, what do you think? The opposite. They're shared equally. Okay, think of it like this. Remember electronegativity? What does that mean, electronegativity? Atom's attraction to other atoms. So if I have a very high electronegativity like fluorine, I am super, super attracted to electrons, right? So let's say, for example, me and Sebastian are sharing electrons. Hold on to this. This is a bond. We're bonding. Okay, 2 electrons. If I'm fluorine and I'm super electronegative, I have a stronger attraction to them. So I'm holding a little bit closer to them, right? Let's say he's a different element. He's like silicon. He has a lower electronegativity than me, but he's still bonded. We're still bonded. Okay, but again, since I have a higher electronegativity, I'm going to pull those electrons a little bit more than him because I'm more attracted to them. So with polar, the electrons are shared unequally. Right now it's being shared unequally because I have a stronger pull. But let's say our electronegativity difference was not large. Remember, 0.4 was nonpolar. So, we have a very equal sharing. That's called nonpolar. The electronegativity difference is not large between us. Does that make sense? Makes sense. Good. So, we can use the electronegativity table to determine the values. I'll give this to you on the test. And you have to use that table to know what's going to be polar and what's going to be nonpolar. So I'll write that out. 0 to 0.4 is going to be nonpolar. 0.41 to 1.69 is going to be polar. And then 1.7 plus is going to be something called ionic, which you should be familiar with from chapter 7. Okay? Now, it's super important that I include all the extra stuff I'm going to write, I'll write later. I'm going to say it and I won't write it now, I'll write it later. Okay, but basically, the atom that exhibits the highest electronegativity has the strongest attraction. For me, for example, when me and Sebastian were sharing our electrons, I was fluorine, I had more electronegativity, so I had the strongest attraction. Okay, now, what happens in polar molecules is something called a dipole moment. Like what? Watch this. Okay, I have this molecule, HCl. When it's super what? Yes, 2 poles, yes. So HCl is a molecule for, a hydrochloric acid is the name of the molecule. So HCl is hydrochloric acid. Okay, I want you guys to tell me if this bond is nonpolar, polar, or ionic. In order for me to do that, I need the electronegativity chart. So I'll give you the values. Hydrogen is 2.1. Chlorine is 3.0. I have to subtract these to get something called the electronegativity difference. Okay, what's 3 minus 2.1? 0.9. Where does 0.9 fall in my scale? Polar. So this is a polar bond. Okay, something you should know about polar bonds. All polar bonds form a dipole. What does that mean? Again, remember when me and Sebastian were sharing our electrons? I was holding it a little bit closer to me than him. What charge are those electrons? Negative. So if it's closer to me, could you say I'm slightly more negative than he is? Yeah. So we use this symbol called delta to represent slightly. Partial. Okay, so chlorine in this case is more electronegative, right? So he's going to have the stronger attraction. So he's going to be partially negative. While hydrogen is going to be less negative, but we say positive. With this dipole in place, right, we call it dipole. We call it dipole because there's two poles. What's a pole? An electrically charged region. So I have, here's one pole, here's another pole. This whole thing is called a dipole. Good? Again, all polar bonds form a dipole. Now, let's look at this molecule. This is carbon dioxide. I'm just going to draw it. I'm not going to explain how. This is carbon dioxide. Let's say I asked you guys, all right, help me find the polarity of these bonds. I want to know if this bond is polar, or if it's non-polar, or if it's ionic, or I don't know. I want you to tell me. So what do you think you would do in order to determine if it's polar or non-polar? Use the table, right? But what do you need? Yes. So if I told you that oxygen was 3.5 and carbon was 2.5, what would you do? And then? What's the difference? Good. So according to my table, where does 1 fall into this table? Number 1? Where is it? Polar. Perfect. So this bond is what? Polar, right? Good. Okay, so I have this polar bond. Well, can I check the other side? Will it be the same or different? Same, because it's the same element, right? Same electronegativity. Does that make sense? So it would be a difference of 1, and this whole bond would be what? Polar. So this bond is polar. This bond is polar. So wouldn't you assume the whole entire molecule is a polar molecule? And fortunately, it's not. Okay, and I'll explain to you why it's not. So I'm going to make you all of you stand up. No, I need 2 of you, actually. 2 of you to stand up. Thank you. Alex, Sebastian, stand. Okay. 1 here, 1 there. We are going to make CO2. If I'm in the middle, who am I? I'm C, and you guys are who? You're oxygen. Hold on to me. Okay? So you both have an electronegativity of 3.5. So you should be pulling on me at the exact strength. Does that make sense? Am I moving anywhere? No. Am I staying in place? Are you guys sharing our electrons equally? Yes. But what if you change into nitrogen, right? When you're nitrogen, he's going to have stronger pull. So he pulls on me stronger than you. Is this equal? Is this equal sharing? No, this is a polar molecule. But since both of you are oxygens on both sides of me, you guys pull on the most equal amount. So that's why I'm not moving anywhere, right? I stay the same. This is a non-polar molecule. Does that make sense? So what I like to think about is I think of tug of war. I look at my central atom, I think of tug of war. If both of the elements are the exact same element, they're going to pull the same. And my carbon is not going to move. So the whole thing is going to be shared equally, which we call non-polar. But let's say I were to add some random element on top, like hydrogen.
Why would it be non-polar if you're not moving?
Right.
I thought
No, so the moving thing is like hypothetical. They don't actually move. But
exactly, but it's not like if it's shared equally.
right. So
Nothing is unshared unequally.
yes. So non-polar is when they're shared equally. Does that make sense? I know it's confusing. You think nonpolar, not equal. But nonpolar means they're equal. Polar means they're not equal. So you guys were pulling on me equally, right? So the whole CO2 is actually nonpolar, even though the bonds are polar. Okay, but let's say I added a random hydrogen on it. He has an electronegativity of 2.1. So then I have my oxygen pulling this way equally, my oxygen pulling this way equally. Will it be equal pulling from this side? No, because his value is what? 2.1. It's much lower. So carbon's going to be like pulling nicely, and then he's going to be like pulling backwards from the hydrogen. Is that equal? No. So now the molecule's not as polar. Sorry. It's shared unequally. So that's how you can determine polarity. Linear. Oh, with the hydrogen? Trigonal planar. Okay? Perfect. Does that make sense, guys? Okay. All right. It's still recording. I'm surprised. Imagine it's not recording the whole time. I would kill myself. I'm joking. Okay, so next thing. We're on the last topic. Electronegativity? No, we already did that one. Attractions between molecules. Okay, so attraction between molecules. So I need you to understand, if I were to have this random molecule, right? So this is our chlorine and our hydrochloric acid. And then I drew another guy over here. I'm drawing another molecule. Okay? Sometimes they can interact with each other. They can get some type of attraction. Okay, intermolecular forces are what that called. Intermolecular forces are the interactions between different molecules. So these two different molecules, they can interact in different ways. Whether it be, magnetically or whatever it is, they can interact. There are 3 types of intermolecular forces. Hydrogen bonding, dipole interactions, and van der Waals forces. Okay? Or also called dispersion. Same exact things. Okay, you're like, what the hell are you talking about, Miss A? Watch. Can you remember the HCl we had before? Remember how it was polar? I had a slightly what on this hydrogen? And him? What if I had another HCl next door? This is also what? And this? So what do you think happens between this guy slightly negative and this guy slightly positive? They like to be attracted, right? What happens with opposite charges? They attract. So we have an attraction going on here. Again, what is this called when I have 2 poles? And what are they doing? That's called a dipole interaction. Good? Okay. Hydrogen, van der Waals. Van der Waals is the stupidest force in chemistry. It's so useless. It makes no sense. I'm going to try my best to explain it to you. It's such a reach. Van der Waals happens to everybody. It's the weakest force. Hydrogen is the strongest force. Okay, you see the document's messed up right now. You see how it's so messy? Okay, because I'm trying to save time. If I try to make it nice, it's going to take longer. I'm going to make the document nice with all of the stuff there after, and I'll send it to you. Okay, but anyways, van der Waals. This is an atom. This is an atom. Atoms have electrons. Atoms have electrons. They move very fast. They move very fast. Okay? If one atom's electrons decide to move over to the right side of the atom for 1 second, you know what happens if it's next to another atom? It what? Okay, yes. So these electrons are negative. So what happens if this guy has electrons over here? His electrons are also negative. Well, these negative electrons, they don't like being near each other. Does that make sense? So this guy, when he has his electrons on the right side, it's going to push these guys to the other side for a second. Okay, so let me erase this. Let me move this guy. So all of these guys, they move over here for 1 split second. You're with me? So now that all these guys are on that side because they're repelling against each other, I have more negative on this side, right? So I could say that this side of the atom is slightly negative, and this side is slightly. This side is slightly. This side is slightly. So what happens for a split second between the two sides? That's it. They get attracted. That's van der Waals. Dispersion forces. When the what do you mean? It doesn't matter. What do you mean? Is that what you said? Yeah, great question. It's a split second of attraction, but it's constantly happening. And like all of the atoms in every molecule, it happens to them. All you need to know is that every single molecule has dispersion forces. That's why it's the weakest, because everyone has it. With hydrogen bonding, or with dipole, for dipole, you have to be polar. That's important. For hydrogen bonding, you have to be polar, and you have to have hydrogen. So it's more, there's more requirements for that bonding, so it's stronger. So what do I mean by hydrogen bonding? Okay, let me give you an example. I'm drawing you water molecules now. Here's a water molecule, here's a water molecule, here's a water molecule. Okay, good. I drew 4. Oxygen has a electronegativity value of 3.5. Hydrogen has a value of 2.1. I want you to tell me if this bond is polar or non-polar. How do you know? What is 3.5 minus 2.1? And 1.4 on our scale, where does it fall? Yes, so that's why it's polar. Good. So because it's polar, what do all polar bonds form? A dipole. So if I go back to over here, these elements are going to form a dipole. If this guy has an electronegativity of 3.5 and this one's 2.5, who's going to be the slightly negative one? Perfect, because he's more... I always forget how to draw the symbol. He's more electronegative. Does that make sense? And hydrogen's going to be slightly positive because he's lower in electronegativity. So that makes this guy also what? And then this oxygen's also what? This guy? This guy? You got the idea, right? Perfect. So then what happens is that, do you see how I have the negative oxygen and the positive hydrogen? What are they going to do? Get attracted. What was this called again? Dipole interaction, yes? Okay? But the thing that makes this hydrogen bonding, oh my God, what did I write? Hydrogen bonding is, I have a hydrogen, right? And in order for it to be considered hydrogen bonding, it has to be attached to the big 3. Nice. Who are my big 3? N, O, and F. They're the big 3 because they're the highest in electronegativity on the periodic table. Okay, so when I have my hydrogen attached to a big 3, and he's attracted to another big 3, that's called hydrogen bonding. Does that make sense? Okay. It's the strongest force that we have. Okay? And those are the 3 forces. So we have the dipole, the hydrogen bonding, the van der Waals. And again, hydrogen bonding is the strongest, while van der Waals is the weakest. And that is it. Yay! I'm so proud of you guys. You did so good. Okay. And I'm gonna edit this document, make it look much nicer, and I'll share it in the group chat, or I'll send it to you guys, okay?